Hi there, and welcome once again to another electricity lesson. In this one we're looking still at resistance, and this time resistance in parallel. So in the previous video we had a look at resistors in series, and this is an example of a resistor in series. Remember, series means the branch or the resistors are in a current that did not split from the original current. So here's the original current going all the way, gets to the resistor, and in the process of getting there it never split up into a different branch of the circuit. So in this case, since there's only one resistor, my total resistance is equal to that one resistor. My total current, okay, since the current is measured not in a split, then that current here would be equal to the total current. So the total current at this point, or let's start with the voltage. Okay, the total voltage is the amount of energy that is given per coulomb as the coulombs leave the battery, and as they get to the resistor they can spend all of their energy at this resistor because it's the only resistor. So here we would see that the voltmeter reading on here, the total voltmeter reading here would be the same there because all of the energy is spent at that point. And now we get to the current. The current would at any point in the main branch be the same as the current that leaves the battery. So the current that leaves the battery is the same as the current that enters the resistor because there's no split. So there's the total current would be equal to the initial current. That with one resistor, this is all very easy, and we can find this total current by saying simply the total current is the total voltage divided by the total resistance. So this is a very important point. If I wanted to know what is the current that passes into resistor 1, I would have said the current in resistor 1 is equal to the voltage over resistance 1 divided by resistance 1. But in this case, since all of these values are equal to R1 is equal to total resistance, voltage 1 is equal to total voltage, then also we can conclude that the resistance, the current that passes into resistor 1 is also equal to the total current. Okay, but that we've looked at that quite sufficiently. So what I want to do is now just add another resistor into the system and see what effect does this have. Now the first thing you need to notice is that the moment I do this, the current I1 cannot be equal to I1 cannot be equal to, and therefore cannot be equal to the total current anymore. So let's now make a distinction. We need to add now another ammeter here to measure the total current. So this is ammeter reading AT. I'm going to call it AT because that's going to be literally the total current. How many coulombs pass at this point every second. Now the problem is once it gets to this point, and now let's add an ammeter here as well, and let's add a voltmeter reading here as well. So voltmeter 2, because this is resistor 2. Now you'll notice that once I get to this point here, my current splits. All of the coulombs can't pass this direction, and all of the coulombs don't go in that direction. There's a split happening, which means that now, and sorry I numbered this one, should be 2. Okay, now what I should know is that, okay, now my total resistance is this, my total current is the current that goes to resistor 1 plus my current that goes to resistor 2. Now how would I work out what is the total current? Well, total current would be my total voltage divided by my total resistance. And my my current in here, what would the current be in this branch? Well, it stays the same. The current in that branch is equal to the voltage that has to be spent, the energy that has to be spent in this branch, divided by the resistance in that branch. Okay, so if there's more than one resistor in this branch, we will add that resistance, okay, plus the voltage. So now I'm at I2, at branch 2, divided by the resistance in branch 2. So again, if there's another resistor in branch 2, this resistance 2 will not just be R2, but we'll add up all of those resistances. Okay, so now I just want to show you something that's very important, and we spoke about it when we talked about potential difference. Remember, the voltage represents the amount of energy that each coulomb has. When they split, the amount of energy that each coulomb has did not reduce. This one's the voltage per the energy, the joule per coulomb stays the same, even though it splits. Okay, yes, there's fewer passing a certain point at this point and passing a certain point at that point, but the joules that each one has is the same. So what is important is to remember that the total voltage divided by total resistance is equal to voltmeter reading at 1 and voltmeter reading at 2 will be the same as the total voltmeter reading in the end, and that is simply because the joules per coulomb in each branch is the same. So voltmeter reading at 1 will be total voltmeter reading divided by R1, plus voltmeter reading at R2 will be equal to the total voltmeter reading divided by R2. And now you'll notice that if I divide, this is an equation, if I divide every term in the equation with VT, I will get rid of VT. Okay, so if that will leave me with a 1, so I'm multiplying with 1 over VT. Every term gets multiplied with 1 over VT. 1 over VT. I'm allowed to do that. Okay, I hope you know that. Now I find the following. Okay, now this is very interesting because in series we had, when something was in series, then my total resistance used to be equal to just adding the resistors together. Okay, until I get to my last resistor, however many there were. But this time my total resistance in parallel is calculated using this expression: 1 over R1 plus 1 over R2 plus, and this goes on for however many resistors I have in series, in parallel. Okay, now if we go and look at the current readings on these two, how will we find the current readings on these two? Now, if I look at the current, let me just change my color. Okay, if I look at I2 would be equal to the voltage in branch, I1, let's look at I1, I don't know. I1 would be the voltage in I1, divided by the resistance of R1. Okay, or at least the total resistance in this branch. If there was another one, I would have to add all the resistors in that branch to know what is the current in that branch. Okay, and the same goes for I2. To get the current in I2, I will get the total resistance or the total voltage in I2, or voltage in I2, and the resistors, the total resistance in branch 2. And that will give me the current. And then once again, we just know that if we add these two together, we will get the total current. Okay, if we add these two currents together, they must give me the total current. But what I do want to show you, and the reason why I'm showing this again, I've shown it there as well, is that notice that if resistor 1 is bigger than resistor 2, the voltages are the same, because remember, voltage in parallel is equal to the total voltage, because it simply represents how much energy does each coulomb have, and whether it comes out here and whether it splits, the total not voltage, total energy that each coulomb has would be equal. So this is the same as saying take V total divided by R1 and take V total divided by R2. So the two branches doesn't have different voltage readings, but they might have different resistor readings. So if resistor 1 is bigger than resistor 2, we're increasing the denominator, which means same numerator but different denominator, which will mean different currents. Now if R2 is then bigger, it will reduce the fraction. If I increase the denominator, I reduce the fraction, which means I am reducing the current. And again, it makes sense. When the electrons come here, more electrons will go where there is less resistance. If we had a stream of water, there's two streams. One stream has a big rock in it. Another stream has absolutely no, let's say it makes a little island here in the middle, which means the stream splits up into two. Then more water will be flowing in the path with least resistance. There will be water flowing here, okay, it's not blocked, there will be water flowing, but if we measure the current at this point and we measure the current of the water at that point, okay, you'll definitely see the side with the least resistance has the highest current, and that is again just demonstrated by the calculations here. Now finally, let's just look what is going to happen if I add another resistor in, and let me do it as quick as possible, another resistor. So now we have 3. In other words, I'm asking the question, what will happen when adding resistors in parallel? Will that increase the total resistance, or will it decrease the total resistance? Well, I'm adding another resistor. Doesn't that just mean I'm increasing the total resistance? Well, let's look at the calculation. If I look at this, I have to rewrite it because here I'm working with a fraction. So the way I will rewrite it is I will say, okay, I have to first, this is a calculation, I have to first add up all these fractions. Now it's a little bit difficult because we don't necessarily have values, but I need to have a common denominator for them all. So I think what will make it the easiest is just by looking at 2 resistors for now. So let's look at 2 resistors for now, and if I were to add these two together, if I had to calculate the total resistance, this is what I'll do. I'll add these two fractions together, and that will give me R1 times R2. So I'm trying to get a common denominator. This first denominator did not, or the first denominator did not have the R2, so I must multiply with R2 top and bottom, and that gives me R2, and the next one didn't have R1, so I have to multiply with an R1 top and bottom, and that gives me R1 times 1 is just R1, so plus R1. So you'll notice now that I've got 1 over RT. I've got a fraction equal to a fraction, but I want to know the inverse of this fraction. I don't want to know what is 1 over RT. I want to know what is RT. Now I can do that by, for example, if I say 1 over 2 is equal to 2 over 4, that's the same as saying 2 over 1 is equal to 4 over 2. Okay, so if I swap the one side of the fraction, I can swap the other side. I can't do it from the beginning. Okay, notice that this, I can't say RT is R1 plus R2 plus R3, and let me demonstrate that. A quarter, a half, are 2 quarters, 1 quarter plus another quarter. I can't say that 2 is equal to, now I just flip them around, 4 plus 4. That's not true. I first need to add the right hand side, and if I do add the right hand side, I get 1 over 2 is equal to, if I add these two together, I get the 2 over 4, which is what I had here, and I demonstrated that that is true. 2 divided by 1 is equal to 4 divided by 2. So just notice you can't just flip the fractions around. It doesn't give you the same answer. You first have to add the right hand side, and then we can flip it around. So then we can now say, okay, that means R, actually I want to change the color, that means RT is equal to, and I flip this fraction around, R1 times R2 divided by R1 plus R2. Now if we were to add another one here, and I'm not going to show you all the steps for time's sake, but if we were to add another resistor, it would just mean we have a plus 1 over R3 here. Now each one of these needed to be multiplied with an R3, which means each one at the top now gets not just multiplied with R2, it also has to multiply R3, and this one gets multiplied with what it didn't have. It didn't have R1 and R2, so it will change this expression to be R1 times R3 plus R2 times R3 plus R1 times R2, and in the numerator we'll have now an extra 1 R3. So notice now what has happened. The question is R1 times R2 divided by R1 plus R2 compared to R1 times R2 times R3 divided by R1 R3 plus R2 R3 plus R1 R2. Which one would be bigger? Again, we saw that we increased the numerator. Okay, so the numerator has been increased by multiplying with R3, but the denominator has also been increased by multiplying with R3, R1 with R3, R2 is also multiplied with R3, and we've got another factor here, R1 times R2, which we didn't have here. So here the denominator has increased much more than the numerator is increased. The numerator was only multiplied with R3. The denominator was multiplied, every term was multiplied with R3, and we had an additional factor of R1 times R2. Now again, you don't really need to know all this if you can remember what I'm going to show you in parallel. Adding resistors in parallel will decrease the total resistance. Why decrease? Because my denominator increased more than my numerator increased. And if my denominator increases more, my numerator, the whole fraction will decrease. So adding a resistor will decrease the total resistance. Total voltage will stay the same. Okay, total voltage is simply how much what would the reading be on there? Well, it would be the same, because the same amount of energy is expended per coulomb. Okay, and then the total current is equal to the total voltage divided by the total resistance. Now, if total resistance decreased in a fraction, if the denominator decreases, the fraction itself increases. Okay, that's what inversely proportionate means. So if my total resistance increases, I will have that my total current or if my total resistance decreases, my total current will increase. So it's got exactly the opposite effect than it has in series. Okay, so let's look at our diagram here. What would happen to current if I added a resistor here? If I add another resistor here, well, if I added a resistor here, I am increasing the resistance in this branch, which means if I increase a resistor in a branch, I'm adding a resistor in parallel. Adding a resistor in parallel, now just notice, now this voltmeter reading and that voltmeter reading will be different. Okay, remember that the voltmeter reading tells me how much energy is expended in each resistor. Now initially when it came out here, okay, and it comes to this point, the amount of energy per coulomb, joule per coulomb, is the same for going into this branch and going into that branch. But the coulombs that go into this first branch has two places to spend their energy. The first resistor and this third resistor. This would be number 3 because we number this one number 2. So voltmeter, if I have a voltmeter reading 3 here, these two added together will give me the total voltage here. Why again? Because voltmeter readings in parallel is equal to the total voltmeters, but these two are now in series. So the total, if I were to take the potential difference between this point and that point, then I am definitely going to have the same reading as over this point and that point, or this point and that point. Okay, I'm sorry, I might be confusing you now, but what I want to show you is that adding a resistor here in series, I'm adding it in series, but I'm adding it in a parallel branch. Okay, so in doing that, I've increased the resistance of a branch, which will decrease the resistance, the total resistance, which will this one here, the current here, will decrease, okay, but the current here will increase. The reason why this current will decrease here is because I've got more resistance now here. So as my current passes, fewer are actually going to pass in that direction. More is therefore going to go into this, and even more is going to go into that direction, because my total current has even increased because my total resistance has decreased. But once again, thank you very much for watching. I think that's enough said on resistance in parallel. I really hope you learned something. I really enjoyed teaching it, and I'll see you in the next video, and probably in that video I'll be doing some complicated, simple to complex examples. We'll see you.